In this class, we'll discuss on the topic quantum key distribution. Why quantum key distribution? Because the classical cryptographic algorithms relies mostly on the hardness of the computational part, whereas quantum computing might thread the known RSA and the ECC algorithms. Though quantum key distribution offers the theoretical security, the security part is mostly guaranteed by the law of quantum mechanics. So a lot of research goes into quantum cryptography as quantum computing evolves because the hardness of the existing classical cryptographic algorithms is questioned by the parallelism effect of quantum computing. Having said this, we have an quantum cryptography model, which you call it as a quantum key distribution model, where Alice is a sender which prepares quantum states, transmits it through, and Bob on the other side receives it. The quantum channel for transmission can be photons in terms of quantum physics, and in terms of quantum computing, we call it as qubits. A normal quantum key distribution model, communication model, is where Alice, the sender, you can have a quantum state generator. We'll see how it works out, and that helps you to encrypt the plain text generated by Alice. We send the encrypted text through an public channel, which is received by the Bob, decrypted and used. Now, there are various quantum key distribution algorithms, and one main algorithm, which we call it as BB84 algorithm, which is proposed by Bennett and Grassat in the year 1984. They, for encrypting the plain text, use two conjugate bases, which they call it as rectilinear and diagonal, which talks about the polarization part of 0 degrees and 90 degrees onto rectilinear, and 45 degrees and minus 45 degrees onto the diagonal basis. So with this information, we'll try to understand how this works. It's all based on quantum physics, on polarization of a single photon, where it gets shifted to any one of these angles. So how do I convert this polarization state or depict the polarization state? We take two gates, the normal X gate and the Z gate. Z gate goes in for a phase flip, where the polarization states on the Z base is indicated by ket 0 and minus ket 1, whereas on X basis it is ket plus and ket minus. So the quantum states are 4, where we have taken the conjugate and we have also represented. Now, how are we going to do it? Alice wants to send a set of bits. Now, this Alice begins with a random set of bits, and either she can apply an Z base or an X base. So this X base and Z base is selected by Alice. So for the first 0, Alice has selected Z base. Second 0, Alice has selected the X base. So it is purely on her selection or the selection of the sender side. Now, what do we do? Based on the bases we select, we try to send the quantum bits, which is ket 0, ket 1, because when, if you remember, if I select Z base, for 0, I'll be using ket 0. For 1, I'll be using ket 1. If I use X base, then it is ket plus and ket minus for 0 and 1 respectively. So with this information, if it's 0 on Z, then it's ket 0. 1 on Z, it's ket 1. 0 on X, it's ket plus. If it's 1 on X, it's ket minus. So these bits are sent from the Alice perspective. On to the Bob's side, Bob receives the values what are being sent, and Bob chooses the base at random. It can be Z or X, and it has been applied. You receive a set of values over here. Now, if you look at the first bit, Bob has selected Z on 0, which results in 1. And then X on, now here, if you just look at it, she has chosen Z, and this person has chosen X. The measurement, what is applied is get minus, and still they get the same answer, which is 1. But in the fifth part, it is 1 and X, where we have chosen Z and we have received get 0, which results in 0. So Bob takes an measurement at random. He randomly measures each of the bit based on the basis. So what Bob normally does on this receiver side is we use random basis. Now we have to handheld the Alice and Bob, the sender and receiver has to handheld by sharing certain secret bit. So how does it really happens? We share a shared secret key between Alice and Bob. Now, how do we share it and how do I identify the secret key? Though I receive something, the secret key is the values which we have received as correct by applying the correct gate. So 0, we have received 0, both have applied X, so I'll select this. This is Z and X, I'm not going to select it. This is X and X, the value is same. Whatever you have sent is the one you have received. So such kind of values will be selected. So 00101 acts as the secret key. Now the next one is, and you try to update it, ensure that Bob tries with different bases, ensure that he receives the correct information which is sent by Alice. But if there is an intruder who tries to receive one and tries to manipulate it, then how are we going to tackle it? So we have to go ahead with error mechanism, and then we have to work it out. So what happens is Alice sends the base and the get 0 value. So Z with get 0, Eve receives it. Now Eve have two options: either to use Eve updates gets the value of get 0 on 0, and now Eve can apply Z with get 0 and with half the probability, and the other half is she can choose an X base. If Z base is obtained, it is being received by Bob. The same what has been sent by Alice is received by Bob, and the presence of Eve goes undetected. But what happens if Eve choose X gate? There is possibility of get plus and get minus. If it is get plus, again Bob receives Z get 0, and the presence of Eve goes undetected. And when it is get minus, Bob receives Z and get 1, where among all these probability, 1/4 probability, Eve, the presence of Eve is being detected. Now, this is all about what I have explained so far. Now, what is the probability of Alice and Bob detecting Eve? Now, among the how many number of bits can we share? We'll take one bit after the other. And for example, if Alice and Bob shares 50 bits secret of their shared secret key, where the number of bits which is transmitted would be 256 and plus 50, which is the shared secret key. The probability of going undetected is 3/4 over 50. So the probability of Alice and Bob detecting Eve is 1/3, 1 minus 3/4 the whole power n. If we share 50 secret bits, then it is 1/3 minus 3/4 the whole to the power 50, which is the way you detect Eve is 0.999 probability, which is very close to detection. Fine. So this is how the BB84 algorithm performs it. Now, we have few assignments. We'll try to understand how it works. Now, you have Alice bit, Alice base. You are supposed to find out what Alice sends. X on 1, X on 0, and then which is you have your get plus, get minus, get 0, get 1 to be uptime. So you can submit this as an assignment. Similarly, you have the base, Bob's base and Bob's measurement. The second question, Bob bit is also presented. Now Alice has a set of bases. Try to identify the secret key where you can try with the common gates, what are being applied, and that acts as the secret key for your kind information. Fine. Is BB84 alone the protocol? No, you have E91, which works on quantum entanglement, whereas BB84 doesn't work on quantum entanglement. This is just for an information. We are not going into it deep. B92 is also another protocol which works on non-orthogonal states, which means the states which are not separated by 90 degrees. Okay, the vectors which are not separated by 90 degrees. Again, this is not part of a syllabus. The security principles of quantum key distribution are based on the no cloning theorem and the characteristics of quantum states where the measurement disturbs it, and eavesdropping leads to detectable errors to the percentage of ideality. The common attacks on quantum key distribution are intercept reset attack, photon number splitting, man in the middle, and detector blighting attack. Fine. How do I do the performance evaluation? We have some terminology called as quantum bit error rate, where we talk about the number of error bits by the total number of bits. And your key is secure only if the ratio of QBER is less than the defined threshold. Fine. So that's it for your quantum key distribution.